Sir, we can.
All right.
Yes, sir. We can start now.
All right, will do.
Okay, delegates, welcome to next session.
All right, so we are
On whole life carbon assessment, setting boundaries. Sir will be taking the session. Yes, sir. Over to
all
you, sir.
right. Thank you so much. Appreciate that. So, basically, we are technically in day one, session 3. If we talk about the inauguration session, so we're now going to start deep diving into whole life carbon assessment. As you can see, as per the schedule, this is where we're going to discuss important aspects of whole life carbon assessment, which include system boundary, the reference study period, RSP, and other aspects. So I'm going to begin by giving you some basic information first, and then we will move into more detailed discussion. Okay, so before I go any further, what I want to do is talk about whole life or life cycle assessment. What is LCA? Because that is the core. LCA is a technique that is used in various sectors, not just construction. So LCA is a method which is used to assess environmental impacts associated with all stages of a product's life. So originally, this is designed for products. So let's say if you are manufacturing perhaps any kind of product, you can think of a product like a chair or a table. You can do a life cycle assessment, LCA, and be able to get environmental impacts from that product over its entire life. Now, this has to be extended to products, services, and in our case, to buildings. So that's where we will move. But first, we need to understand the fundamental of an LCA. So LCA takes into account all types of environmental impacts associated with the extraction of the raw material, its transportation to the manufacturer, its actual manufacturing, its use, and its disposal. So sort of cradle to grave analysis can be done using LCA. It's been standardized using two major ISO standards. If you're very interested in theoretical aspects of LCA, then you can look at 14040 and 14044. It's used across industries. So it's used for products, used for services, and we are now applying it to buildings and infrastructure. It helps identify trade-offs, hotspots, and opportunities for improving the environmental performance. Okay, so that is the main reason why we use LCA. So why is LCA important? It is important because it helps us make environmental decisions. And these decisions should not be based on one stage of the product only. Like in construction, right now, most of the decisions we make for upfront construction process separately, and then when the asset is being used, we make decisions separately. LCA, as the name suggests, helps you look at all the product stages, all service, or in our case, life cycle stages of building or infrastructure projects. It supports sustainable product and system design. It enables evidence-based policy and procurement, and it aligns with net zero and circular economy goals. So that's why LCA is extremely important. The key life cycle stages in a study that we will undertake will basically be raw material extraction. So maybe from a mine, maybe from any other source, including harvesting, and then the transportation of that raw material to a manufacturing facility. Any emission that takes place, so let's say you have a huge stone aggregate quarry where you have heavy machinery, heavy transportation equipment, all the emissions coming from those equipment will be calculated. Then the manufacturing process itself, so for example, you're manufacturing steel or you're manufacturing cement, all emissions that take place in that process are also counted. Then you actually, the use phase in which you operate, maintain, or repair, and then end of life in which you demolish, recycle, and dispose of those products. So these are the broad life cycle stages that are made part of a life cycle assessment. So therefore, this is where we start talking about whole of life assessment of buildings and infrastructure. So the core components of an LCA, broadly, irrespective of which sector you're working in, are first to define the goal and the scope of your assessment. So what is being assessed and why? Then you need to have life cycle inventory. This is the data collection for inputs, outputs. So energy, materials, emissions, all that information. So you need to have lots and lots of data when you're doing LCA. The third step is life cycle impact assessment. You then take the environmental impact indicators, the data, and convert that into environmental impact indicators. LCA is broad. It looks at various environmental impacts such as carbon emissions, acidification, and other aspects of impact, environmental impact also. And fourth step is obviously to interpret the results of the analysis and allow its use by decision makers. Now, we have adopted or adapted LCA to carry out whole life carbon assessment in the built environment. These are the adaptations that we have done. First, WLCA for us right now only focuses on greenhouse gas emissions. So it only focuses on CO2 equivalent when we do our assessment. So that's the first change we have made from a generic LCA to a WLCA for our sector. We've designed it such that it can be applied, the LCA can be applied to both buildings, so vertical or to horizontal infrastructure. It covers all aspects of emissions, and we are going to be discussing the various aspects of the emissions, such as embodied and operational emissions. It increasingly is becoming required by clients, regulators, and green building certifications. As you saw in LEED 5.0, there is a need for you to do WLCA calculations. Other certifications similarly are requiring WLCA to be done. It sets the stage for us achieving net zero or near zero carbon buildings. So LCA being a generic sector agnostic approach, we adopt it to our sector by making these changes. So, as I said, the LCA that we carry out in our domain only looks at GHG emissions. Greenhouse gas emissions refer to the release of gases into the atmosphere that trap heat and contribute to the greenhouse effect, which is the process by which Earth's atmosphere warms. So we are focusing on GHGs. Broadly, the GHGs, as per the Kyoto Protocol and the Paris Agreement, are carbon dioxide, CO2, methane, CH4, nitrous oxide, and a whole bunch of fluorinated gases such as hydrofluorocarbons and so on. So our LCA only focuses on GHG and these greenhouse gas emissions. So when we talk about GHGs, we are talking about these gases. The assessment that we are making is about GWP, or the global warming potential. So an LCA can be utilized to study a whole range of environmental impacts, as I said, eutrophication, acidification, GWP, and so on. Our assessments in the construction sector primarily are going to focus on GWP. So what is GWP? The IPCC definition of GWP is a measure of how much energy the emission of 1 ton of gas will absorb over a given period of time relative to the emission of 1 ton of carbon dioxide. So the larger the GWP, the more that a given gas warms the Earth's atmosphere compared to CO2 over that period. So typically this period is considered to be 100 years. Okay. Again, we have adopted it slightly in the ISO and EN definitions, where we use it to calculate do LCAs. An important category to refer to the embodied greenhouse gases of a specific product or product level GHG emission intensities. So we further modify GWP. So when I'm doing WLCA calculations for a building or a bridge or a transportation project, I am essentially focusing on GHGs and calculating GWP values. So how do you actually calculate GHG and GWPs? Now, the gases that I just described are called the Kyoto gases, because that's when this was agreed. All measurements of GWP are generally done. So you will basically loosely, we will always say carbon emissions or carbon or emissions, because all we are doing is we are calculating GWP in terms of carbon dioxide equivalent. So CO2e, for example, or CO2 equivalent, or sometimes written as CO2 EQ. So this is what that equivalent means. The main gas, which is carbon dioxide, has a value of 1 GWP. So it has 1 kilogram carbon dioxide equivalent. Methane gas, on the other hand, has 25 GWP. Nitrous oxide is 298, hydrofluorocarbons, HFCs, PFCs, SF6 and NF3, these are the fluorocarbons, they have these values. So basically, if you release nitrous oxide, it's going to be equivalent to 298 carbon dioxide equivalent. So basically, what we want to do is always calculate GWP in terms of carbon dioxide equivalent. So global warming potential indicates the amount of warming a gas causes over 100 years. So typically it's GWP 100. All of this, again, may seem confusing. You can get more information. Slides where I have additional sources, you can always see them here. So let's look at what this really means. So the carbon dioxide equivalent is our measure of GWP. So from now on, whenever we do an WLCA for a building, we are going to be calculating emissions in terms of carbon dioxide equivalent. So carbon dioxide equivalents are commonly expressed as million metric tons of carbon dioxide, also written as MMTCDE. But all of this, let's bring it to some relevance. Now, a typical petrol car, gasoline car, this is US data produced by EPA, would emit in 1 year per kilometer, sorry, it emits 250 grams per kilometer of carbon dioxide in its tailpipe. That is what it's emitting. It emits 0.01 grams per kilometer of methane, 0.00225 grams per kilometer of nitrous oxide, and negligible fluorinated gases. Okay, so if I go and look at these numbers, methane is 25 times the carbon dioxide equivalent. So even if I multiply it by 25 to get my carbon dioxide equivalent, and 298 times for nitrous oxide, I will still get a very, very low number compared to, these are going to be very low. So my carbon dioxide equivalent per kilometer of a car, gas car, or a petrol car running is 250.01 grams per kilometer. Okay, so this will give you a typical passenger vehicle emits 4.6 metric tons of carbon dioxide equivalent per year. Okay, so this is, all these calculations are shown in the Environmental Protection Agency, EPA, US EPA website on this link. So the point I'm trying to make is our unit of measure is going to be carbon dioxide equivalent, but we loosely say carbon emissions, carbon dioxide emissions, but technically it means carbon dioxide equivalent, CO2e, which, as per these two slides, this is how you calculate it. But you will really not have to go into these details because we will always be calculating like this. So in this case, for a car, we have calculated 4.6 metric tons of carbon dioxide equivalent per year. Okay, so there are various dimensions to our measurement now. Today, we are only going to touch upon this, but then we will go into much more detail. When we measure emissions across the supply chain, we call them Scope 1, Scope 2, and Scope 3 emissions. Okay, Scope 1 emissions are directly associated with an organization and its facilities, its vehicles. Scope 2 emissions are basically purchased energy emissions that come from it. Okay, so Scope 3 is all your supply chain emissions. So most construction emissions are going to be Scope 3 emissions. So your site demolition, site excavation, because this is going to be done, if you are the developer of a building, you are going to get subcontractors, contractors, vendors, suppliers do all the supply chain work. So the emissions caused by construction itself, material production, construction, maintenance, repair, operational energy use, water use, all of them are traditionally Scope 3 emissions. So if you are measuring emissions from your assets across the supply chain, we distinguish or categorize them by Scope 1, Scope 2, and Scope 3 emissions. But what we are going to be doing initially is we are going to be calculating emissions across the life cycle, the production of the materials, products, systems, assemblies that go into our buildings or infrastructure projects. That is stage 1, production. We'll measure emissions across stage 2, which is construction, stage 3, which is operation, stage 4, which is end of life, and stage 5, which is beyond asset life cycle. So we will account for all these 5 steps for a building or a bridge or any infrastructure project. During production, we will look at emissions that come from raw material extraction, their transport, their manufacture. We will then look at construction, transport, assembly, and installation. We will look at operation, use, maintenance, repair, and renewal. Then we look at end of life, deconstruction, waste processing and disposal, and then any beyond asset life, things like reuse, recycle, and energy recovery. So this is how our assessments will work. We are going to look at the first stage, which is product stage. So for your building, every product that is used would have to be calculated for raw material extraction, raw material transportation, raw material manufacturing using that raw material, the construction product. Then we will measure emissions from transporting all products, bricks, paint, carpet, doors, windows, to the construction site, its installation, the emissions that come from that. Then when the building is complete or the bridge is complete and it's being used, all emissions that come from its operating it. So like this building in which you are, the lights, the air conditioning, any elevators, any escalators, all the energy use, water use will be accounted for. Emissions resulting from the use of those, any maintenance and repair, and then end of life. Within this assessment that we do, we are going to be categorizing further. Remember, if we do across supply chain, it is scope 1, scope 2, scope 3. When we do across life cycle stages, we are going to categorize emissions into embodied carbon, operational carbon, and user carbon at the very least. There are more, and I'm going to go over that also shortly. So the scale and scope of assessment that we have to do for buildings and infrastructure projects is 3 levels. You have to do LCA at the whole building or infrastructure level. You have to do LCA at the complex assembly level. So let's say you have an air conditioning system which has ducts, it has other units, the condensing unit, compressor, all other diffusers, air handling units, and all those things. All of that will become a assembly or a complex component that also we need to do LCA on. And then you perform LCA at the basic material level also, because if your building uses, let's say, timber, you need to have its LCA in order to do the whole life LCA. Or maybe first you will do the LCA for a truss or a wall, and then the whole house. So these are the 3 scales at which you will have to do LCA for our sector. When you do an LCA, you will have to start thinking both as a carbon expert as well as a cost planner. When you think of a cost planner, you have to think in terms of the life cycle of a building, the design stage, pre-construction stage, construction stage, and so on. But if you are a carbon expert, you also need to think, as you just saw, across the product life cycle also, meaning raw material supply, transport, the construction, installation, and process of those individual products and processes. So this is sort of the dimension in which you are looking at. So you're looking at life cycle stages A through D for the building and A through D at the product or scale also. So you have to keep in mind that there is this bi-directional connection between how a cost planner thinks and how a carbon expert thinks. Okay, so before I move any further, I'm going to define the important categories of emissions that we are going to be calculating using our WLCA. The first type of emission that we need to understand is called an embodied carbon emission or embodied emissions. The embodied emissions are from an asset, from a project or an asset, the total GHG emissions that are going to be measured in CO2 equivalent, the emissions and removals associated with materials and construction processes are basically called embodied carbon. Okay, so all emissions related to the product manufacture and construction processes are called embodied carbon. Operational carbon is the carbon which is the emissions that come from energy use and water use in the building or the bridge or the infrastructure project when it is actually in use. So it's completed construction. During the use phase, whatever emissions come from energy use and water use are basically called operational carbon. There's another type of carbon that we're going to be talking about that's called biogenic carbon. These are carbon removals associated with carbon sequestration into biomass, as well as any emissions associated with this sequestered carbon. Most WLCAs, the assessments that you will do, you will calculate biogenic carbon separately and report it separately. So, simple example would be a timber beam. Let's say you're using a timber beam in your project. The carbon emissions or removals associated with that timber beam are called biogenic carbon. Okay, the biogenic carbon is again calculated and reported separately. The last major type of emissions that we are going to worry about is user carbon. Okay, user carbon refers to all GHG emissions, again measured in CO2 equivalent, associated with the user's utilization of the buildings or infrastructure during its use stage. Okay. So, user carbon, imagine you guys came to this building for this meeting. Whatever emissions you caused while coming to the building that you are in are called user carbon. Generally, user carbon is an optional calculation. User carbon is optional because it's not directly in architects, designers, constructors, or building operators' hands, right? It is much more to do with urban planning, where the campus is located and where are residential or hotel accommodations available. If you flew into Nagpur, the emissions that were caused because of your travel are also user carbon. So I'm defining it here, but generally it is not part of the calculations. We focus on embodied, operational, and biogenic carbon generally. But it's good to know what is user carbon. And as you saw in session 2, I showed you that emissions from our sector, which are embodied and operational, account for about 43% of the total GHG emissions globally, annually. If you include user carbon, then 79% of the emissions come from our sector, which tells you very clearly that user carbon is very broad. If I use a bridge, if I use a train, if I use a building, whatever as a user emissions I caused are called user carbon. So it's a bigger part of the economy. We don't have direct control on that. Embodied carbon, I have direct control because I can use low carbon material. Operational carbon, I have direct control. I can use insulated walls, I can use other energy efficiency mechanisms, I can use less water, less energy. It's in my control. Biogenic carbon is again in my control. I can use biogenic material, bio-based material, where I can store carbon rather than emitting carbon. So that's why our focus of a WLC is generally on embodied, operational, and biogenic carbon. So this is the layout which we typically use for whole life carbon assessment. If there was one slide out of these 5 days that you wanted to pay attention to, this would be it. Okay, so this slide is the slide that actually tells you how we conduct assessments. These are called information modules. Okay, so you will notice that there is A module, there is a B module, there is a C module, and a D module. So whole life carbon assessments are conducted across 4 modules for buildings and infrastructure. Module A has A0, A1, A2, A3, A4, A5 submodules. You will notice all of them are related to either product manufacture, cement, steel, paint, tiles, or it has got to do with transportation of those materials, or it is directly associated with the construction itself. So module A is product and construction stage. So pre-construction, product stage, and construction stage. Module B is when the asset is being used. So it's called use stage. It has B1 through B8 submodules. Module C is end of life stage. Okay, that is when you repurpose, demolish, or do something else with the asset. So it's the end of life stage. That's module C. It has C1, C2, C3, C4. Module D is beyond the system boundary. It is benefits and loads beyond the system boundary. So any heat recovery, any thermal energy recovery, any reuse, recycle, net benefits are treated in module D. Okay. So if you look at the assessment information, it spans modules A, B, C, and D. Yeah, the building life cycle itself, we consider modules A, B, and C. D is considered outside the system boundary. So let's dig a little bit deeper into this. A0 is called pre-construction, okay, which is basically acquisition of land, acquisition of right of way, and all that. Typically, we assume A0 emissions are 0 for a building. A0 is traditionally associated with infrastructure projects only. Okay. A1, A2, A3 are product stage. You will notice that I'm using a light blue color to further help you understand the various information modules. The light blue color stands for embodied carbon. Okay, so all light blue is called embodied carbon, which we just described. The pink, magenta, purple, whatever you want to call it, B6, B7 that you see in the middle of the slides is your operational carbon. User carbon is B8, and I've highlighted that in yellow. Further, within embodied carbon, I have used a green square in A0, A1, A2, A3, A4, A5. Those signify a subcategory within embodied carbon. Those are upfront embodied carbon emissions. Okay, so A0, A1, A2, A3, A4, A5 are also called upfront embodied carbon. All that you see with blue triangles within the light blue highlight are use stage embodied carbon. So embodied carbon is further divided into three types: upfront, use stage, and end of life. So all the blue triangles that you see, B1, B2, B3, B4, B5, are all use stage embodied carbon. And then gray circles, C1, C2, C3, C4, are all end of life embodied carbon. So top level categories: embodied carbon, operational carbon, user carbon. Embodied carbon is further subdivided into upfront carbon, use stage carbon, and end of life carbon. Okay. If you look at C1, C2, C3, C4, C1 is all emissions related to deconstruction, demolition of your asset. C2 is all emissions related to transport to waste processing of all your disposal or disposal. C3 is waste processing for reuse, recovery, and or recycling. C4 is disposal to waste. So all emissions related to disposal of waste are C4. In many jurisdictions now, in order to get planning approval or permit, as it is called, you are required to do whole life carbon assessment. So you have to think 60 years into the future and estimate what's going to happen at the end of life. So very soon these kinds of regulations are coming, and you as experts in this domain will have to make those estimates of embodied carbon at end of life. Okay, so minor additional clarification. So obviously let's say you're building a simple residential unit. All emissions coming from the manufacturer of the products that you're going to use, their transport is captured in module A. Then you transport all that material to your building site. All that emission is included. Then when you lift stuff with a crane, pump concrete, all emissions in the construction stage are included in A4, A5 in that module A. Now the building, your residential unit is in use. Maybe in 15 years, you will replace the roof, right? So that repair, maintenance, replacement will be captured in B4. So the new roof that you'll place will again have embodied carbon, because maybe you will buy new kind of roofing material and so on. Or maybe you will replace windows, maybe you'll replace doors. All of that is getting captured in B1, B2, B3, B4, B5. That's why in office buildings, when you do a tenant improvement or a fit out, let's say every 5-year cycle, you're actually releasing more embodied emissions because of that kind of retrofit or tenant improvement and those kinds of processes. So all those emissions need to be accounted for. The last thing on this slide, there is another standard which is called PAS 2080, which I should have included in that list, calls embodied carbon capital carbon. Okay, I'm sure all of you have heard of CapEx and OpEx. So capital cost, operational cost, CapEx, OpEx. In the same way, they don't want to call it embodied carbon. They think of that as capital carbon, carbon that is spent during construction, carbon emissions that are released during construction. So you may come across somebody using the term capital carbon instead of embodied carbon. But otherwise, this is a pretty standard. This is based on ISO standard. These are called information modules, and that's what it means when we have been saying since morning life cycle emissions. Life cycles broken into 4 modules, A, B, C, D, further broken down into sub-modules and different types of carbon associated with um, various life cycle stages. Information modules is called embodied, operational, and user carbon. Within embodied, you have upfront, use stage, and end of life. Okay, so typical office building, right? Emissions, we've talked about embodied, operational, and so on. What are the typical emissions? So this is the Carbon Leadership Forum sample building, 30-year estimate over the life of this building. You can see the yellow bars are your upfront embodied carbon. Okay, so about 400 kilograms carbon dioxide equivalent per meter square per year. Okay, so annual emissions. But in year 0, you have 400 kilograms of carbon dioxide equivalent per square meter. Then you have your operational carbon, which you can see light blue and dark blue bars for 30 years. Okay. Uh, in between year 15, you see another yellow bar. That's where maybe the roof was replaced. That's where maybe the new air conditioning unit was placed, or whatever that repair, intervention, maintenance, retrofit, whatever that took place is shown again in that yellow bar. So and the pie charts on top show the breakdown in terms of initial embodied versus operational, over the life embodied versus operational, and so on. There are 2 bars, blue bars. One is a standard performing building, and the other one is a high performance energy efficient building. Um, anyone wants to take a guess? Why do we have decreasing blue bars? Why are they not constant? Because a building, if you meter it, it's going to use the same amount of energy every year, right? Unless we change something. But why is it constantly decreasing? Any guess? Anyone in the room? Any guesses? The reason is that we
Hello.
are, yes, sorry, go ahead.
Sir, what I am getting is we are dividing by that number of years for the total amount of carbon.
No, that's an annual number. So the reason why it's decreasing is that we are assuming that our grid is going to become cleaner. So we are drawing energy from the grid, right? That grid today may be a lot of coal-fired energy generation, but maybe we'll move more and more to hydro, maybe more and more to other renewable, maybe nuclear. So because we are projecting 30 years from today, we are doing a grid decarbonization. So we are assuming that the grid is going to become cleaner.
Right.
So our estimate every year and our standard provides you with that grid decarbonization number. So
So
we
the
are
energy source will become energy efficient.
correct. Yes. So the building is benefiting from the overall economy and the grid becoming cleaner or energy efficient. Yes, absolutely. Okay. So another way to look at it, if you really want to understand very simple, basic, maybe at a concrete beam or a column level embodied carbon calculation, you can go to this simple guidance from iStruct E. Okay, so you can use iStruct E guidance. So if you think about it, it's pretty straightforward what we are trying to do. What we are trying to do is assume that you're doing an WLCA for a column, concrete RCC column. So if you knew the quantity of concrete, quantity of the steel, and if you knew the carbon factors for concrete and steel, meaning 1 cubic meter of concrete releases how much CO2 equivalent, then you can easily do the calculations. If you can do the energy modeling, now let's assume that you're actually doing a single family residential unit. If you can do energy modeling, you can also similarly determine or estimate your energy use. Based on energy use, the government publishes a carbon factor. So for drawing 1 unit of electricity from the grid, you have a carbon factor which you multiply and you get your total emissions. So it's actually a pretty straightforward calculation, but you need quantity of materials, you need energy modeling, you need many data sources to be able to do the calculations. So if you look at cradle to gate, that is your A1, A2, A3. Cradle to gate would mean product at the manufacturer's gate. Then cradle to site would mean transporting all your material to the site. Then cradle to practical completion would mean everything, including construction. Then cradle to end of life would include everything that you have done to this building over its 60-year life or 120-year life for an infrastructure asset. And then cradle to grave would include module C. And then various colors we are using are for embodied, operational, and user carbon. Again, user carbon, not many people calculate. It's difficult to calculate. So, and you can see the breakup of these embodied carbon calculations. So if you just look at embodied carbon, 50% is upfront. Okay, actually 55% is upfront, A1, A2, A3, A4, A5. About 43% is during the use stage, B1, B2, B3, B4, B5, and B6. Actually, just, sorry, B1, B2, B3, B4, B5. And then 2% is C1, C2, C3, C4. So that's the distribution. Okay, so
Sir,
yes.
small doubt here. In the
Uh-huh.
last slide,
Yes.
A5, how we are going to quantify that A5?
So A5 is all your emissions from equipment. So let's say you're running a diesel generator on site. You're running a site office that is connected to the temporary electric and water. You have a tower crane. Maybe you have an excavator. All your equipment, emissions from those need to be calculated during the duration of construction. So A5 includes whatever emissions come from your construction site. In the installation, assembly, worker transport, those kinds of things. We're going to look at it in a little bit more detail, but that's what A5 is.
Okay.
A5 is tough to calculate though. So here in the US, they've just come out with a calculator. Maybe if somebody can keep track of things that I'm promising, I said I'll send a report on carbon pricing. I can also share with you a link, which here in the US, an entity called Associated General Contractors of America, they have released a tool in which you can basically measure your emissions during site operations, so A5. But again, it's pretty straightforward. If you're running an excavator for 200 hours, every hour there is this much emission, you multiply it by 200, and let's say you're using 5 excavators on site over a period of 2 years, you will then be able to calculate your emissions. Right? Make sense?
Yes, sir. So if we are doing that in situ construction, maybe for column, shuttering or some shoring, or we are using that material will also come into this.
Correct. And the pump, concrete pump, or whatever lifting mechanism you're using.
Got it, sir. Thank you.
Okay. You may use a concrete compactor or vibrator, so you will have any emissions from that. So every piece of equipment should be accounted for, but people don't go into that much detail. There are thumb rules available because you'll have to use waste factors, you'll have to use many other things, but there are thumb rules which we can look at later, where you can more rapidly go into calculating. Remember, it's a very small portion of the overall. It's only about 1% roughly, A5, right? So you don't want to spend too much time in going into a lot of detail. Okay, so how do we carry out an assessment? You have an infrastructure project. You have been made the leader to run an assessment on that infrastructure project. Big picture, how would you go about carrying out that assessment? So this flow diagram shows how the assessment is carried. Start at the first start block. Step 1 is to set your goal. What is the purpose of your assessment? If you don't know the goal, you don't know the performance criteria, maybe if you don't know the target, there's no point in running the assessment. So you set the purpose and the goal of your assessment in step 1. Step 2 is very important. This is where you define your assessment. This is called step 2 scope. This is where you're going to define the scope of your assessment. The scope is defined by using 5 dimensions. Step 2A, you saw the information modules, right? So you select which information modules are applicable to your assessment. Maybe you're only assessing the impact of replacing the roof. Maybe then only module B is what you really need to look at. So which information modules you need to select. That's how you define your assessment. Obviously, that is determined by the goal, and the scope therefore is connected. Then you select in your definition of your assessment, you select when to carry out an assessment. That's step 2B. Our standard, for example, asks you to, at the very minimum, do a concept stage, a construction stage, post-construction stage, and then maybe a use stage assessment for your project. So you have to determine how many assessments will you carry out. One is not enough, remember, because if you're doing a new build, early on in the project, you may not have enough information. By the time you're doing construction, you will have actual information. So you estimated 1,000 cubic meters of concrete, you poured 1,050 cubic meters of concrete, so you need to run the assessment again. Then you have to set up the assessment period. You saw in the examples that I gave 30 years. In the UK, the assessment period is for buildings is 60 years, and for infrastructure, it is 120 years. Step 2D, you're going to define spatial boundary. So you basically will define what is included, what's excluded in your assessment. In step 2E, you're going to determine which elements you're going to study. Is it the foundation? Are you including MEP? Are you including HVAC? And so on. So all of that becomes the scope definition. The next thing that you need to do is estimate. How much concrete, how much steel, how much paint, how many air handling units, how many lifts or elevators, how many escalators, how much paint, how much tile. All of that needs to be estimated. You also need to estimate your energy use, your water use. So you typically would run an energy model, which we are now very used to. For decades, we have done energy efficiency. Most projects have If you're getting either a GRIHA or a LEED certification, you would do your energy model. So that estimate is also needed. That is your step 3. Step 4 is where you go and collect carbon factors. Okay, so those carbon factors are essentially going to help you determine how you are going to convert the quantities into actual emissions. So if you have 1,000 cubic meters of concrete in your project, you need to collect from reliable sources which are regional or local how much 1 cubic meter of concrete has GWP emissions. Okay, so you need to be able to get that data. Those are called carbon factors. Multiply the two and you have your emissions. Let's say the transport of concrete is 20 kilometers each way. Okay, so you need to also find out carbon factors of or emissions per kilometer of a ready mix truck emitting when it's loaded, fully loaded, and when it's returning empty, so that you can estimate the emissions associated with transport from the gate to your site, right? So all those carbon factors are needed. How much emissions are there per unit of energy that you use, per unit of water that you use? That is a big exercise. Step 4, collect carbon factors. Step 5 is to actually conduct the assessment. Step 6 is to produce the results, interpret and report results. Obviously, technically the assessment ends here, but this is then going to be taken into a decision-making process. Maybe you'll have to repeat the whole assessment with a different option. Let's say you had a different type of window. Now you want to have a triple glazed window. You can run the whole assessment again. So that's what you basically would do, the overall process of your assessment. Okay, so now let's go step by step. Goal of the assessment. You can have multiple goals. You could be doing an assessment to compare design options and products or materials. You're doing the assessment to make end-of-life decisions. You can run assessments to comply with the regulations. As you just saw, New York Local Law 97, you need to do WLCA. Greater London Authority, GLA, if you want to do a new build, you want to get a planning application approved, you have to submit to WLCA. So your assessment goal could be any of these, combination of these. You may be running an LCA to document the environmental performance of your building. Maybe because you're looking for an investor who's interested in low carbon projects. You could be doing the assessment to fit into maybe LEED V5 or maybe to a low carbon building initiative labeling scheme. So goal can be any of these. These are some examples. Remember, I said I'll give you more details. This is the more detailed modular information structure or information modules that you need to then select. As I said, A0 pre-construction, typically 0 for buildings used for infrastructure. A1 is for your raw material supply. A2 is for transport. A3 is for manufacturing. A4 is for transport from the manufacturer to your site. A5 is for construction and installation processes. It can be further broken down into A5.1, any emissions resulting from demolition, if applicable in your project. A5.2, from all construction activity, pouring concrete, painting, perhaps lifting materials, excavation, everything. A5.3 is from waste and waste management. Typically, you have waste factors. If you're applying plaster, there is some waste factor for ceiling, for walls, paint, same way. A5.4 is for all your worker transport. This is again generally applicable to infrastructure projects where workers are moving around from a distance into your construction site. So that's your A5.4. B is B1 is in use emissions. So these are B1.1 material emissions and removals, like from refrigerants. So any fugitive emissions from refrigerants are B1.2. You may have blown insulation. Any emissions caused because of that released from your construction materials are generally counted under B1.1. B2 is maintenance, B3 is repair. You will be able to pick and select which modules apply to your assessments. These are taken from the RICS standard, but they are directly compatible with EN 15978. So B0 is generally 0, B8 is optional. We would normally not calculate the user carbon, which is shown below. So let's say now you have set the goal, picked up your information modules. Now you have to decide when you're going to carry out the assessment. It's generally minimum 4 times during the project's life cycle. During the concept design stage, so very early on, remember early in the project, you have minimal information, but you still want to calculate cost and carbon. So the concept design stage. Then you do it at the technical design stage when you have detailed design information. Then you should repeat it at the construction phase and then post-completion phase. Varying degree of information is going to be available to you, but post-completion phase, one major difference is you should use metered information for your B6 and B7. So the water energy use, water use should be from your meters. In the concept, technical, and construction, you can use your energy models. Next comes the assessment period. It's also called the RSP, reference study period. So you basically are looking at RSP, which is very crucial because remember, we are doing an estimate into the future. So in order to compare between buildings, between options, you should be using the reference study period. Reference study period generally varies by various nations. So in the UK, as I mentioned, it's 60 years RSP for a building. So if you're doing an assessment for a building project, you have to do 60 years worth of calculations. If you're doing it for an infrastructure project, it's typically 120 years. So just think about it. You're estimating 120 years into the future. So it's a tricky task. Yeah. Spatial boundary is the next thing that you fix. It's typically the property line, sometimes called the red line, because you want to make sure that you're including in your assessment. Maybe there is some infrastructure project, site development, landscaping, maybe some paving, maybe some parking. You want to make sure that you pick the property line as per your local jurisdictions, based on regulatory or national standards. So that's something that you have to set. Then you have to pick what entities you're going to include. So let's say it's a mixed-use development or it's a transportation network. It may have rail, road, may have stations, it may have a major interchange and so on. Those entity types would also need to be selected. So you can see there are various types of infrastructure projects that you can also do assessments on. When doing an assessment, you can use this concept of projects and sub-projects. So basically, you can have multiple sub-projects within a mixed-use development or a large transportation network. The elements of the study. So what are you going to include? Your building or infrastructure would have sub-assets. You can include those. Then you have to include element categories, elements, or sub-elements. So draw a work breakdown structure or work package and decide which elements you're going to include in your assessment. Is MEP included? That's probably the hardest to do because there's not much data available on MEP products, systems, and components. So again, part of scope definition would be to pick the elements of the study. Then you're going to go and estimate and forecast. So you will have an energy and water use model plus your BOQ. You can use BIM, you can use a digital twin, you can use any other technique you want to use. Maybe you would require the help of an estimator, cost consultant to get you this information. Maybe you'll need an energy modeler required to get you the energy and water use for your project. But this is the stage where you have to calculate quantities, figure out plant and equipment, figure out how many workers, waste, how many kilometers you're traveling. All kinds of data needs to be collected. This is called primary or foreground data of your assessment because it's directly linked to your project. Any questions before I move forward? No? Okay. So another busy slide, and we're going to go over in the session tomorrow in more detail. So now what do you have? You have a BOQ. Okay. With that BOQ, you can multiply with carbon factors and you can come up with your emissions, embodied operational biogenic emissions for your project. Okay. But remember, we said we're going to do concept stage assessment, technical design stage assessment, construction stage assessment, and then a post-completion stage assessment. Obviously, at the concept stage, you are not going to have details about which mix of concrete, how much steel is being used. You will have very high-level information at that stage. So at that stage, you would need asset level benchmarks. How do we do cost estimating in a concept stage? Rupees per square feet, dollars per square feet, right? But for different building types, different floors, different specifications. There's a lot of historical data which we use to do early cost estimates. Similarly, in carbon also, we need those benchmarks. We need that historical data, but that's missing. So it's a pretty tricky situation. Kilograms of carbon dioxide equivalent per square feet of school buildings. If you had that, you could use parametric modeling to estimate, early estimate of your carbon emissions also. But that is the data that's missing. We are trying to build a database, the built environment carbon database, as you see at the bottom, which is from where you can get these kinds of benchmarks. But then, as technical design is completed, you now have much more information. At this stage, you need carbon factors. So if you knew you have 100 cubic meters of concrete in your project, and if somebody told you, like here, these are called EPDs, right? So if somebody told you in Nagpur, this type of concrete, this is Heidelberg, probably I picked up this sample from North Vancouver in Canada. If you knew what kind of mix it was, like this one, 30 MPa, 20 millimeter non-aerated Evo build bronze, ready mix of Heidelberg from concrete BC, you can get this document like on a tin of food, you get nutrition values, same thing. You're getting GWP potential for 1 cubic meter of concrete. This is called a declared unit. In the declared unit, so this is that declared unit. GWP is 231 kilograms of carbon dioxide equivalent. It's very similar to somebody saying concrete, 1 cubic meter of concrete is equal to X rupees. So you can calculate the total cost of concrete. Same way you can now calculate emissions coming from the concrete that you're using. There is more information: ozone depletion potential, acidification potential. Remember, we are not doing that. We are only focusing right now on GWP. So for you, this number is needed. So hypothetically, if you can collect EPDs or these kind of labels for all products in your building, you multiply that, those carbon factors, you will get, you can then get your emissions for your building. But you have more pieces of information that you need. There is a CIBC standard called TM65, which can be used to do embodied carbon calculations for MEP, because getting EPDs for MEPs is very difficult. You can look into the Global Logistics Emissions Council to get emissions from transport, from logistics. So if you're shipping material 400 kilometers from a location A to your site, you can use emission carbon factors from the GLEC. So countries like in the UK, they publish, the government publishes carbon conversion factors for energy use, water use, for running a truck or a concrete mix. So all that carbon factor is really needed for you to be able to do these assessments. Once your assessments are done, you use this kind of a template to report your carbon emission. So you can do a subtotal, but eventually you can also provide benchmarks such as X kilograms of carbon dioxide equivalent per square meter of building, per kilometer of single lane highway, per parking unit in a parking structure, and so on. There are different reporting templates. This is provided by RICS. It's Excel. You can download. This one is for buildings. This one is for infrastructure projects. You will notice for infrastructure, you can do A0 also. Okay. So wanted to run a Q&A, but that Q&A is not running. Let me try it one more time. Okay, I guess we need to continue. So if anyone has any questions, please let me know. You should be seeing on your screen or on Slido, I guess. Here we go. So if you scan here or go to slido.com, I guess it is. Continuing, so it will store the question answers for our entire session, which is fine. Okay. Thank you very much. What gaps? Any other questions? Sorry, this is becoming complicated. How much time do we have?
It seems almost like done. 3:30, like another 4 minutes are there for your session.
Okay.
Yeah.
So,
if you have any question, please come forward. If they are okay, or maybe after good food. They will be-
I hope you guys had a good day. If there are no questions, I'm going to pause here and pass over to Dr. Alegankar. I'm going to actually disappear because I think I got to go and take a quick nap, if you don't mind. Is that okay?
There's one question which is appearing.
Sure.
The participant has asked, is there any permissible embodied carbon range, like a benchmark?
Yes, there are benchmarks. We will share some of those benchmarks with you. I have benchmarks from the UK, from Canada, so for office buildings, for school buildings, and most jurisdictions are going to publish and say your new building cannot exceed this limit. So we will be sharing those targets with you.
Yeah, okay. So with this, maybe we can conclude for first two sessions, and we look forward for your notes, sir. Also,
Yes, I will email the PDFs so that everyone has the PDFs and let's compile things that I promised to give, links and all, and I will start sharing those.
So my team here, they are trying to frame some questions.
Okay.
Within couple of days, we'll post you those questions. You may review them, and then last day we can have the exam for all the sessions together.
I'm glad you brought that up. Remember, folks, there is going to be a quiz on Friday. If you want your certificate, you have to pass the quiz.
Yes.
So please, hopefully you're paying attention. Those who are online as well as those who are in the room. So thank you. I'm going to sign off now.
Yes.
Probably need to take a little break before my day job begins.
Yeah. So
Thank you.
for next sessions, you will get another link.
Sure.
It will be posted to you in due course of time. Thank you, sir.
Thanks. Thank you. Bye.
Okay.
Bye, everyone.